Viewers, today in this video we will learn how to do animations in GeoGebra application of a 2 degree of freedom system like that you are seeing now on the screen. So let us start learning. For this case we will take 2 points P and Q, both of which will move in the plane. Here we will consider a 2D coordinate system or a planar coordinate system. So like the x-axis and the y-axis. Next, now we will take 2 points. First we will take the origin of the coordinate system O, then we will take 2 points. One is point P, which is here, another is point Q, which is here. Next, we will join O and point P and point Q, both will be moving in the plane independently. So like this, so that basically we will use the concept of position vector for such animation. Now we will, if say this, if this length is say A, if the length of the OP is say A, and length of PQ is say B, and the angle made by the vector OP is say theta, with the x-axis, and the angle made by the line PQ is a phi with the x-axis. So that is this angle is phi, say, then we can write the coordinate of P as P equal to, so P is equal to A cos cos theta comma A sin theta. And if we want to write the coordinate of Q, then we will write Q in terms of P. So Q is equal to P plus this. So the coordinate of Q is incremented taking P as the reference. So from P or relative to P we will define the position of Q. So Q is equal to P plus, in the same way as, now it will be B cos phi comma B sin phi. So that way we will basically define Q. So there will be basically here two parameters. One is the angle theta for the rotation of point P about the origin O. Another is phi, which will be used to rotate Q about point P. So that is the concept behind the animation that we will do here. So here you see that here I have given a length for the vector OP, another length for the vector PQ. So there are two lengths, and also there are two independent angles theta and phi. So you can see the animation that we are doing here. Now we will do the calculation from starting. So here you can see that I have defined an angle theta here. So here you can see on the left side of the screen, theta I have defined varying from 0 to 360 degree. Another angle phi I have defined from 0 to 360 degree. Both are measured about the positive x direction. Now I have taken here two lengths P, the two lengths A and B. Here I have taken sample lengths. One is 10 units, that is A is equal to 10 units and B is equal to 5 units. You can take any other values. Here I have fixedly defined. In the earlier video I have shown how to define differently and use that in the equation. So I am not repeating that part since you can do that. So follow the earlier video for that variable length for the radius that you can do. Now so P is defined in terms of that A, that is 10, and the angle theta. So r theta, in terms of r theta, here you see that from this to this, that is a blue color line, has the length 10 units, and the angle measured from the x direction is theta. Currently it is 67 degree, that you can see, and the red color line is having a length of 5 units, and the angle made by this line measured from the positive x direction is now 280 degree. So it is rotated like that. So in the counterclockwise direction, that measurement is done. So here in the GeoGebra graphing calculator, we can use that as a vector command. So here vector OP, that is the starting point and the end point, here you can see. So the U vector, that is the blue color vector, is done using the vector command vector OP, and the red color line that you can see here, the color, so it is done with starting point P and end point Q. So that is done, and Q is done using the radius of 5 units and the angle phi. So now if we rotate, then if we try to animate that, then we can do that. Animation can be done using the slider command that I have shown you in the last video how to do it. Here in the settings, you can do slider. In the slider, minimum angle and maximum angle can be set here, and here the options can be chosen, either oscillating or increasing or decreasing, like that. So that can be selected for both the angles independently. So here theta and phi both are independent angles that we will rotate point P and Q independently. However, here since point Q is defined, you see in this fourth equation, as Q is defined in terms of P, therefore point Q or the vector PQ will rotate about point P. So that is the conception behind rotating a point or moving a point about another moving point. So here point Q is moving relative to another moving point P. So I guess you understand this concept and you can do it yourself. So do it in the graphing calculator version of the GeoGebra application. Do it yourself. And the concept is the concept of position vector. So position vector of Q is measured relative to the position vector. The position vector of Q is measured relative to the position vector of P, and when we animate or change the angle theta and phi sequentially, then we can get the animation. Thank you. Another thing that I want to show you here is that if we select the tracer points from here, so if we select the tracer points Q and P, then we will be able to see their trajectory or their locus when they rotate. So let us see that how it changes. let us give different colors so that we can differentiate their trajectories. Now we will select these. Now you can see a nice pattern here. Another thing you can observe is that here I have taken for theta the speed 1x and for phi 5x. That means the angular speed of the vector PQ is 5 times that of the vector OP. If we reduce the speed of PQ, then the trajectory will be different, that you can see. If we use the same angle, then you will see they will change. This is having the 1x. Here their relative positions remain same. If I use 2x, let us see that. If you use to 3x, so this is 3x, 3 times the speed. I'm sorry here. This is 3x, the speed of theta. So this way you can change the speeds and get different patterns or trajectories. Thank you for watching.